One thing that we can use conditional expectation for is to compute regular expectation. There's an equation I'll show you that relates regular expected value with conditional expectation. So first of all, let's recall a couple of formulas that we know. One way we can write probability of A is we can write it as a sum of probability of A given BI, probability of BI. Assuming these events BI are mutually exclusive and exhaustive. This might be useful if we don't immediately see the probability of A, but we find it easy to compute the probability of A given BI. And a variation of this is the probability that a random variable x takes a value little x is, we can write this as the probability that x equals little x given some other random variable capital Y equals little y times the probability that capital Y equals little y. So this is the same thing. A is the event that capital X equals x, and BI is one of these events, y equals little y. So if we find it difficult to compute the probability that capital X equals little x at face value, and easy to compute the probability that capital X equals little x given that capital Y equals little y, then we can do this a bunch of times and add them together and get the probability that x equals x. Now I claim that we can do something similar with expected value. So the expected value of x equals a sum of the expected value that capital X equals little x given that capital Y equals little y times the probability that capital Y equals little y. So it looks a lot like this formula, except we have expectation for two of the probabilities. And this could be useful if we find it hard to see what the expected value of x is, but it becomes an easier problem to say what the expected value of x is. I'm sorry, this is the expected value of just x given that capital Y equals little y. So if we find this conditional expected value to be easier to compute, then we'll compute it, multiply by a couple probabilities, add everything together, and we'll get expected value of x. All right, to prove this, let's look at the right-hand side. The sum over values little y of the expected value of x given that y equals little y, probability that y equals little y, is, well, we have a summation formula for this conditional expected value here. So this is a sum over all values of x times the probability that capital X equals little x given that capital Y equals little y. Probability y equals little y. Now this conditional probability we can rewrite as a fraction. This is the probability that capital X equals little x and capital Y equals little y divided by the probability that capital Y equals little y. And if we do that, we see that these two probabilities cancel. Then we can play with the order of summation a little bit. We can move the sum over x outside of the sum over y. We can move x outside the sum over y also, because it doesn't have any y's in it. And then on the inside we have sum over y, probability that capital X equals little x and capital Y equals little y. But if we sum all of these together, this is just the probability that capital X equals little x. We essentially get rid of all the y's by the summation. And now this simple sum is just the expected value of x. So indeed the right hand side is equal to the left hand side in this claim. Now some people write the identity in this claim a little bit differently. So some people write this identity, which is the conditional expectation identity, as expected value of x equals expected value of x given y. Now I think this is a little bit unhelpful. You'll see this in all the books, but I think it's unhelpful because every one of these expected values means something different. So the left-hand expected value is sort of an x expected value, which means the sum of x times the probability that x equals little x. Then this expected value is an expected value over y, because the inside expected value ends up being a function of y. So this is, I might write, e sub capital Y, expected value of x given y, which is a sum of expected value of x given y, each one multiplied by the probability that capital Y equals y. So what the probability here is what I'm using in the subscript. And then the inner expected value here this is a conditional expectation. And that is a sum of values of x times the probability that x equals little x given capital Y equals little y. So the fact that this is a conditional probability that we're multiplying x by is why I put x given y as a subscript in the expectation. Now when I look at this, I don't know, I just think this is very complicated to remember what each of the different expectations mean, because we're multiplying different things by different types of probabilities. And I find this expression of the identity, which is the exact same thing, a little bit easier to work with. Right, so let's do some examples, and I'm going to use this version of the identity to do the examples with. Let me write it right on top. So we have it there to work with. In the first example, I want to consider a mouse that's in a maze. So these are examples when the conditional expectation is easier to compute than this. So we'll compute these and add them together to get the regular expectation of x. So mouse is in the, let's say, central chamber of a maze. So here's the central chamber. There's one path that leads to the exit. It takes 3 minutes to get there. And there's another tunnel that just leads back to the central chamber, and that takes 7 minutes. And then there's another tunnel that just leads back to the central chamber, and that takes 5 minutes. And the entrances to these chambers are all indistinguishable. So when the mouse gets back to the starting point, it just chooses one of the 5 doors with probability 1/5 each. And for simplicity, let's say including the one that he just came out of, which is silly. A human being wouldn't do that, but let's say the mouse doesn't know any better. So each time the mouse returns to the central chamber, it chooses a door each with probability 1/5. Let's let x be the time required to exit, or let's say the time until the mouse exits. So the time it takes for the mouse to get up here to the exit. And let's let y be the door chosen first. So let's let the doors be 1, 2, 3, 4, 5. Let's find expected value of x. Well, this is going to be expected value of x given that the mouse chooses door 1 times the probability that the mouse chooses door 1 plus the expected value of x given that the mouse chooses door 2 times the probability that the mouse chooses door 2, etc., up to the expected value of x given that the mouse chooses door 5 times the probability that the mouse chooses door 5. Now the probabilities y equals 1, y equals 2, up to y equals 5 are all 1/5. Alright, let's see if we can simplify some of what's here. So we've got all the 1/5. How about the expectation parts? So if the mouse chooses door 1, that's the one that goes to the exit, and the mouse leaves in 3 minutes. So we know very well what the expected travel time is. If the mouse chooses door 1, it's 3. So 3 times 1/5. Now if the mouse chooses door 2, then the mouse spends 7 minutes going around in the path and then comes back and is in the same position again as at the beginning. So the travel time is 7, the expected travel time is 7 plus whatever the original travel time is given that the mouse is starting here. And actually if the mouse chooses door 3, the exact same thing happens. There's a 7-minute travel time to get back here, and then the problem essentially starts over. So let me say 2/5. So there's a 2/5 probability that the mouse takes a walk in the 7-minute tunnel and then ends up at the beginning again. And similarly, if the mouse chooses doors 4 or 5, the mouse has a 5-minute walk before getting to the beginning of the problem again. All right, so expected value of x is what this is. All right, well, this doesn't give us the answer for expected value of x immediately, but it is one equation and one unknown. So maybe we can solve it for that one unknown. So let's see, we have expected value of x equals 3/5 plus 2/5 of 7 is 14/5 plus 2/5 expected value of x plus 2/5 of 5 is 2 plus 2/5 expected value of x. All right, so if we take away the 2/5 expected value of x and 2/5 expected value of x, 4/5 expected value of x from this side, take it away from both sides, that leaves us 1/5 expected value of x on the other side. 5/5 minus 2/5 minus 2/5. So on the right hand side we have 3/5 plus 14/5 plus 10/5 for a total of 27/5. So if 1/5 expected value of x equals 27/5, we can multiply both sides by 5 and find that the expected travel time is 27 for the mouse, 27 minutes. All right, now let's do another example that's rather different. There's some problems where what we're doing roughly is taking the expected value of a random number of random variables. So there's 2 bits of random in there. So let's do a problem a little bit like that. All right, let's say an urn has 3 blue and 7 white marbles. And a coin is flipped 3 times. Y equals the number of heads. And then Y marbles are chosen from the urn. And X equals the number of blue chosen. The question is, what is the expected value of X? So here, the expected value of X is easier to compute if we know how many marbles are chosen from the urn in the first place. So this is a good opportunity to use the conditional expectation identity. So let's see, we're flipping the coin 3 times. So Y could be 0, 1, 2, or 3. The expected value of X is the expected value of X given that Y equals 0, probability Y equals 0, plus the expected value of X given that Y equals 1, the probability Y equals 1, plus the expected value of X given that Y equals 2 times the probability Y equals 2, plus the expected value of X given that y equals 3 times the probability y equals 3. Now if we're flipping a coin 3 times, the probability of getting tail, tail, tail is 1/8. And the probability of getting one head, well, that could be HTT or THT or TTH. There's 3/8 probability of getting one head. And for the same reason, there's 3/8 probability of getting two heads, one tail and two heads. The probability of getting all three heads is 1/8. Okay, so we know all the probabilities that y equals this or that. Now if y equals 0, no heads, that means that we're choosing 0 marbles from the urn. So if we're choosing 0 marbles, obviously we're not getting any blue marbles at all. So this is just 0. Now for the other one, we have to think about what distribution could this be, where we choose a certain number of marbles from an urn and then count how many are blue. So this is a hypergeometric distribution. So we need the expected value of a hypergeometric distribution. So let's just recall how that works. So if z is hypergeometric with, let's say, m good objects, capital N minus m bad, so capital N total, and we're choosing n. So m good objects, capital N minus m bad objects, and we're going to choose capital N. Then z is the number of good chosen. So the expected value of z is, it's a little bit like the binomial expected value. It's basically n times p. N, the number of times we're choosing, times the fraction of good ones in the urn. Little m over capital N. Alright, so how does that relate to this problem? So the number of marbles that we're choosing depends on what happened with the coin flips. So let's let z be x given that y equals I. So this is hypergeometric with, well, the number of good objects in the urn is 3, and the number of bad ones is 7. Total is 10. And then we're choosing I of them. So the expected value of z is the number of choices, the number that we're choosing, and the fraction of good ones in there. So I times 3/10. Alright, so this should be what we need to fill in everything else here. So the expected value of x is 0, which we'll omit. And then the expected value of x given y equals 1. So if I equals 1, this is 3/10 times the probability y equals 1. We said that's 3/8. The expected value of x given y equals 2. So that's 2 times 3/10. And again, probability 3/8 of getting y equals 2. And then if y equals 3, we've got 3 times 3/10 times the probability that y equals 3, 1/8. So this equals 9/80 plus 18/80 plus 9/80ths. So 18/18 is 36, and these are both divisible by 4, so that is 9/20ths is the expected number of blue marbles that we're going to choose out of the urn when we do this experiment. And I think this is computable really only if we use the conditional expectations, which are doable. If we just take x at face value, it's hard to see what the probability of getting 1, 2, 3, etc. are. The end.